Hello everyone. In this video, we are going to talk about moment, about its definition, what a moment is, and how can we picturize or visualize this by relating it to our real life. So, if you have read the blog, you must have got an idea, a rough idea about what a moment is. So, let's try to take care of all the examples which we wrote over there and let's see how it looks with respect to some images as well. So moment as we first of all, let's take the first example which we talked about. So let's use up a different uh, thickness. Yeah. So if we are going to talk about example one, we were talking about a regular bench, right? So if this is how that bench looks like, this is the bench, and let's say we just talked about its center of mass as well. So we know that the center of mass of this bench, since it is a regular bench, would be exactly at the center. So we call that this is the center of mass. And let's say your position is somewhere over here. So when you sit over here, obviously, because the gravity is acting on you, so a downward force will act on you, which is in this direction. And this force will tend to have some rotational attribute about the center of mass, which is over here. So we read in the blog that a moment is actually the tendency of any force to cause a rotational movement, right? So and since whenever we talk about rotation, it is always with respect to any axis or a point. So in our case, the axis is over here. So that's actually a 3D axis, which is coming out of the plane or out of the screen. You can visualize like that. So this is the axis about which it tends to rotate, and this is how it looks like. So this is what we talk about the moment. So we'll say that the moment is denoted by m, that is the usual notation, and the mathematical formula for the moment will be F times R, where F is the force and R is the distance from the pivot. One thing which is worth noticing over here is when we talk about the distance from the pivot, it is actually the perpendicular distance. So here we can see that if this is F and this over here is R, we can clearly see that the R is anyway in exactly perpendicular or a 90-degree angle with respect to the force. So this is how the formula of the moment looks like. The unit, obviously the unit of the force is given by, you know, that the unit of the force is newtons, denoted by N, and the unit of the distance, as in the radius, would be meter. So the multiplication of both will be Newton times meter. So this is the unit, or more precisely, the SI unit of the moment. This is how it looks like. Uh, all right. Now let's talk about a little bit about the center of mass as well. So when we talk about center of mass, as of now, our intention is to talk about regular objects. So if we talk about a regular sphere, let's say it's over here, it's a regular sphere. So let's make something like this to give it a 3D touch. For a regular sphere, the exact center would be its center of mass. So if we say that the mass of this regular sphere is m, and we are asked to uh, show that where exactly is the gravitational force acting on this particular sphere. So we'll show on this point only. So it will be mg towards exactly at the center. Uh, Likewise, we talked about the bench. So for bench as well, it was exactly towards the center because that's a regular bench. So it is exactly over here. So this is where the gravitational force acts. So one property which we have is whenever the force acts directly on the center of mass of any particular object, then it does not cause any rotational movement. So if I place a force of F newtons over here, or let's say over here, then that cannot cause any rotational movement. That will just provide a linear movement, right? So this F will not actually be a contribution in the moment. Let's take a new example over here. This is something which we would have observed. Let's consider a door, right? So I'm going to draw a top view of a door. So door is always, choose a different color over here. Door is always moves with respect to a pivot, or we can say it's a hinge, right? So if this is the top view of the door, so the door is over here. This is the rest of the part of the door, and the circle, the dark circle, is the pivot about which the door rotates. Now, consider three situations over here. We apply force to 3 points. One is over here, one is over here, and one is over here. We are talking about the point of pivot, as in this is a point about which the rotation occurs. The magnitude of the force in all the three cases would be same. So where do you think is it is most easy for us to rotate the door? So even in practice, we see that the more closer we are from the hinge, the difficult it is for us to rotate the board, to rotate the door, while the farther we are from the axis, the easier it is for us to rotate the door. So if we talk about this force, this is the farthest from the pivot, since its distance over here is the maximum. If we consider this as R1, if we consider this much distance as R2, and if we consider this much as R3, we know that mathematically, we just discussed that practically this force would be the most easy for us to make a rotational moment, and mathematically as well, the moment is F dot R. If F times R, and we know that for case one, the moment will be FR1, and since R1 is greater than R2 is greater than R3, so if we call this M1, and M2 would be likewise FR2, and M3 would be FR3. So the relation which we have over here is M1 is greater than M2 is greater than M3. So clearly the moment for the first force is highest among all these three. Hence, it is most easy for us to push when we are farthest from the door. Consider a fourth situation when we push, let's say, exactly over here, exactly at the pivot, or let's say the hinge. Will this cause any movement? No, because this practically also we know that if we are going to just push the hinge, it won't really rotate the door. And mathematically, we know that moment denoted by, let's say, M4 is FR. Now, what is R in this case? It is exactly zero, right? Because we are just pushing at the rotational point. So the moment in this case would be zero. So this is getting proved mathematically as well. We also talked about that every moment cause a rotational movement. So every rotation has a direction, and it can be in two ways. It can be either in clockwise, which is denoted by CW, or it can be counterclockwise, which is denoted by CCW. So let's say this is the hinge about which we can have a rotational movement, and this is, let's say, F1, and this is, let's say, F2. So where do you think the moment will cause by the F1? So F1 will cause a moment like this, right? We are talking about this hinge. So this is counterclockwise sense. So we'll say that this is CCW, while a force over here will tend to rotate in this in this direction, and this is nothing but clockwise moment. So every moment tends every moment has a direction. It is clockwise or anti-clockwise. And when we club the two forces, let's say we have another example in which we have multiple forces acting on it. Let's say this is another door over here. This is the hinge. And let's say we have an F1 force acting over here, an F2 force is acting over here, and an F3 force is acting over here. And we are supposed to find the net moment. So if we talk about the net moment, let's say its distance from this pivot as R1, this distance is R2, this distance is R3. Usually we consider a clockwise sense as the positive. So the net moment will be, since this is providing an anti-clockwise sense, this is providing an anti-clockwise sense while this is providing a clockwise sense. So we'll say that moment due to F3 is F3R3. That's denoted by M3. Moment due to the first force will be mind the sign. We are placing a negative here. Why? Because we know that it is counterclockwise. So counterclockwise is usually we are taking it as negative, while M2 will also be negative F2R2. So if we talk about M net as in the net moment, it will be M1 plus M2 plus M3, since the signs are already being taken care of. So we have negative F1R1, negative F2R2 plus F3R3. So this is the net moment in this case. So we saw that moment is actually a static force. It's actually a static force which tend to cause a rotational behavior about a point. We also talked about its similarity with the torque. So we know that torque is actually a rotational force. Let's suppose we are talking about a wrench. So here we have a screw over here and we need to rotate it. And if we are talking about a wrench, let's say we have a wrench like this, and if we want to unscrew it, then obviously we are going to rotate this wrench, let's say in this or the other direction. So this is not actually a static force. This we are providing a rotational behavior by providing a force in such a direction. So that is the actual difference between the torque and the moment. Although if we talk about the unit, let's say the SI unit of the torque, it is also the very same. But if we are going to visualize it, that is the difference between the torque and the moment. So this was all about what a moment can have, just a brief overview. So this is in line with the blog which you have been reading. So I hope this clears up the query, and if you have any more, please get back.